Ever wonder why sometimes when you're, interacting with an AI language model,
Mm-hmm.
it just glitches?
Mm-hmm.
Like you type out maybe half a word and it spits back something utterly baffling, totally unrelated.
Yeah, it's a weird experience.
That's a common frustrating hiccup, right?
Yeah.
And it actually points to a surprisingly fundamental challenge in AI, what researchers are calling the prompt boundary problem.
Exactly.
So today, we're doing a deep dive into a really groundbreaking solution called byte sampler. We're going to try and untangle exactly what this problem is, how it kind of messes with the language model's outputs, and then explore this ingenious new method. It doesn't just fix it, it also unlocks, well, a whole new realm of possibilities for how these powerful AI models can actually work together.
Yeah, and what's truly fascinating here, I think, is how byte sampler addresses this core misalignment, between how we humans see text like a continuous flow and how the language models internally process it chunk by chunk. It's a remarkably precise, elegant fix. Makes AI feel much more intuitive and, frankly, more powerful for us.
So settle in, because as we unpack this, I think you'll find, well, like I did, that the solution is surprisingly elegant. And it opens up some truly mind-bending possibilities. Let's dig in.
Okay.
Okay, so let's unpack the central challenge first. AI language models, they use something incredibly clever and efficient called tokenization.
The basis for most models now?
Right. Instead of processing text, character by character, they break it down into these larger chunks called tokens.
Think of them like Lego bricks of language, almost.
Exactly. Smart prepackaged bricks. Could be whole words, parts of words, punctuation, common phrases.
And this lets them handle huge amounts of text with a much smaller vocabulary. It's efficient.
Super efficient.
Yeah.
It's why pretty much all modern models rely on it. Now, here's where the friction comes in.
Right.
You, the user, you're typing a continuous string of text, right?
Yeah.
Expecting the model to just follow along. But the model's internal process is rigidly tied to these discrete tokens. So the prompt boundary problem, or PBP, happens when your input prompt ends exactly in the middle of what could be one of these single prepackaged tokens.
The boundary doesn't line up.
Precisely. Let's use a perfect example from the research they did. Imagine you're typing into, say, a Llama 3.21b model, and your prompt ends with because.
Okay.
You naturally expect it to complete it with say, to make because.
Well,
But because itself is often a single token in that model's internal vocabulary. And maybe Beck and O are separate tokens it knows.
Ah, I see where this is going.
Yeah, because your prompt ends mid-token, the model gets, well, confused. Instead of predicting say, it might predict something totally nonsensical, like the letter Z.
Wow, Z, that's quite a jump.
It's a complete distortion, a direct artifact of this tokenization mismatch. It's like asking someone to finish a puzzle, but you've given them half a piece, and they just jam something random in the gap.
That's a good analogy. And this kind of mismatch, it isn't just English words, is it?
No, not at all.
It's particularly pronounced in languages like Chinese, where you don't have clear spaces between words. So tokens can cover multiple characters, even whole words sometimes. Makes these boundary issues even trickier.
Right, more ambiguity.
And it pops up in code generation too. Imagine you're halfway through typing a variable name, say document.getElement, and instead of completing with something logical like by-eyed, the model weirdly suggests, I don't know, div. It just doesn't fit.
Completely out of context.
Exactly. The research papers have tons of these examples. An OMO model predicting store instead of T when it's given this a tes.
Right.
Or a Quen model failing to complete a Chinese sentence properly. But then, with byte sampler, it nails it every time.
Okay.
These scenarios really show that deep disconnect between the model's internal token-focused logic and our human sort of byte-by-byte expectation.
So if this problem is so deeply baked into how these models are built, how on earth do you even begin to fix it?
Yeah, it seems fundamental.
This is where byte sampler comes in.
Yeah.
And it's a remarkably clever and elegant approach, actually.
So what is byte sampler exactly?
Okay, so byte sampler is an inference-time method. That's key. It means it works after a language model's already trained and out there. No need to retrain the whole thing.
Which is a huge advantage. Retraining is costly.
Hugely. What it fundamentally does is convert any of these standard autoregressive language models, the ones using byte pair encoding, or BPE, tokenizers, into what acts like a character level or byte level model.
Okay, so it makes it see characters.
Effectively, yes.
Yeah.
But the genius part is, it does this without altering the model's underlying generative distribution at the text level. It lets the model condition its generations on any random byte prefix you type. It completely decouples that awkward prompt boundary from the model's internal token boundaries.
So it teaches the model to see individual characters, even though its internal language is still tokens.
You got it. It bridges that gap.
Okay, that sounds powerful. How does it actually do that?
Well, the core innovation, the real engine behind it, is something called the valid covering tree.
Valid covering tree. Okay, sounds technical.
It is, but it's clever. It isn't just a fancy name. It's a sophisticated dynamic data structure. Imagine like a huge branching tree representing every single possible way the model could complete your partial input, token by token.
Right, an infinite tree initially.
Exactly. Then this structure meticulously prunes away all the branches that don't actually match the prefix you typed. And crucially, it also prunes branches that contain invalid contiguous pairs of tokens.
Invalid pairs. What makes a pair invalid?
A token sequence is only considered valid if the tokenizer could actually produce it from some real-world string of text.
Ah, okay. So it has to be something the tokenizer could actually create through its normal encoding process.
Precisely. Think of it like this. The tree only keeps paths that make grammatical sense to the tokenizer itself.
Okay, and this crooning mechanism, how does that work efficiently?
This relies on a really profound insight the researchers found, specifically for BPE tokenizers. They proved that a sequence of tokens is valid, meaning it could be formed by the tokenizer encoding some text, if and only if every adjacent pair of tokens within that sequence is also valid.
Oh, wow. So you only need to check pairs, not the whole sequence.
Exactly. It's an incredibly efficient way to check validity because you're only ever looking at pairs, which can be done almost instantly. This simple but powerful principle is what lets ByteSampler build and maintain its valid covering tree in real time. It's like a fundamental piece of theoretical understanding that makes the whole system practical.
That is clever. So it leverages the properties of BPE itself.
Right. So let's break down why this valid covering tree is such a game changer. It has three amazing characteristics.
Okay.
First, it's precision or correctness. It accurately captures exactly what the model should predict if it were truly operating at the byte level, aligning perfectly with what you're typing. No more the for because.
So it fixes the core problem accurately.
Yes. Second, efficiency. Despite all this cleverness, it's remarkably light on its feet. The tree's size stays bounded. It only grows by a small, constant amount as you type more characters. It doesn't get bogged down.
Which is crucial for real-time use.
Yeah, absolutely. And third, adaptability. It can update itself in constant time and space every single time you add a new byte to your prefix.
Wow, constant time updates.
Yeah. This combination of precision, efficiency, and that instant adaptability is what really makes it a practical and powerful solution for real-world AI.
Okay, that makes sense. It's not just theoretically sound, it's actually usable.
Exactly.
Right.
So what does this mean for performance, in the real world? The research rigorously compares ByteSampler to other methods trying to fix this PBP issue. They group them into heuristic and exact approaches.
Right. Heuristic methods, things like token healing or various backtracking tricks, they tend to be faster, yeah.
Generally, yes.
But they often come with a trade-off. They might introduce bias or approximations into the output, meaning they don't actually guarantee preserving the model's original sampling distribution.
They take shortcuts.
Kind of. Whereas exact methods, like ByteSampler, are designed specifically to preserve that original distribution, ensuring the model behaves exactly as intended, just at that finer byte-level granularity.
And here's where ByteSampler really shines in the practical application. The data presented in the research, it clearly shows ByteSampler has significantly less inference overhead than other exact methods.
How much less are we talking?
On average, it adds only about 0.72 additional tokens worth of processing compared to just running the plain token-based model.
Okay, 0.72. That sounds pretty low.
It is, especially when you compare it. Another exact method, bypair correction with prefix caching, adds around 2 additional tokens. And an older technique, prefix covering, it adds an astronomical 2.12 times 10 to the power of 30 additional tokens.
Whoa, 10 to the 30. That's
Yeah.
unusable.
Completely unusable. So ByteSampler offers something like 65% less overhead than the next best exact method, which is absolutely critical for efficient, real-time byte-level sampling, especially since you pay this overhead for each byte you sample.
Right, that overhead adds up fast if it's per byte. Okay, so it's efficient. What about accuracy? Does it degrade the model's quality?
Great question. So in terms of accuracy, when they tested it on character-level language modeling tasks for both English and Chinese, actually byte sampler consistently achieved a normalized loss that nearly matches the original token-based models.
Normalized loss, that's like a measure of how well it predicts the next character. Lower is better.
Exactly. Lower means it's less surprised, doing a better job, almost like reading your mind. Byte sampler's performance here shows it effectively fixes the PBP without degrading the model's fundamental language modeling quality.
That's the key, right? Fixing the glitch without breaking the model.
Precisely. And what's more, it consistently outperforms those faster heuristic backtracking methods in next character prediction accuracy.
Ah, so it's more accurate than the faster approximations too.
Yes. It proves it avoids those sampling inaccuracies and weird artifacts that the approximate methods can sometimes introduce. You get reliable, precise text generation.
Okay, so it's accurate, efficient, and solves the core problem. That's impressive.
It really is. But byte sampler isn't just a clever fix for a frustrating problem. Its ability to convert these BGE tokenizer models into byte-level models, effectively unifying their vocabularies, unlocks several truly exciting and, I think, innovative applications for how we can use language models.
Right. This raises a really important question for anyone working in AI, doesn't it?
Yeah.
What suddenly becomes possible when models that previously couldn't really talk to each other because their internal tokenizers were different can now communicate seamlessly at this unified character-by-character level?
The implications are pretty profound.
Yeah. So what are some of these applications?
Well, one major one that immediately springs to mind is byte-level ensembling.
Ensembling, combining models.
Exactly. Traditionally, if you wanted to combine the predictive power of multiple language models to get even better performance, you were kind of stuck if they used different tokenizers.
Right. Their internal languages were just incompatible. Apples and oranges.
Totally. Byte sampler completely changes that. It makes direct combination possible by converting all of them to act like byte-wise models first.
So you can average their predictions at the byte level.
Basically, yes.
Hmm.
The research shows that an ensemble, a combination of models like Qwen 3, Olmo 2, and Llama 3.2, even with their different tokenizers, can often outperform the average performance of those individual models working alone, sometimes even beating the best single model on certain tasks.
Wow. So you can build like a dream team of AIs, each maybe a specialist, and they can now collaborate perfectly.
That's the idea. Another incredibly powerful application is byte-level proxy-tuning.
Proxy-tuning. Okay, what's that?
This lets you transfer really valuable post-training capabilities, things like instruction following, or the ability to generate step-by-step chain-of-thought reasoning.
The skills models learn after their initial huge training run.
Exactly. You can transfer those skills from one smaller, specialized expert model to a much larger general base model. And here's the kicker. You can do this at inference time without needing to spend huge resources fine-tuning the base model's weights again.
Wait, at inference time, without retraining? How?
Byte sampler makes it possible by unifying their vocabularies. It allows the logic differences, which are basically the expert model's preferences or biases for certain outputs that capture its specialized knowledge.
Okay, like it's secret sauce.
Kind of. It allows those differences to be applied accurately across models, even when their underlying tokenizers are completely mismatched.
That sounds revolutionary, actually.
The results they show are genuinely profound. For instance, the research demonstrates proxy-tuning a Llama 3.18b model using a smaller Olmo 2.1b instruct model as the expert. The combined system consistently outperforms the base Llama model on its own.
Okay, expected maybe.
And it even outperforms the smaller, already tuned expert model.
Wow. So the big model gets the expert skills but performs even better.
Yes. What this really points to is a new way to separate the raw quality of a large base model from the specific training recipes used to give it certain skills. It makes it dramatically easier to apply diverse, specialized training techniques to any large base model, no matter its original tokenizer.
So a base model could gain nuanced instruction following or complex reasoning abilities from an expert without that expensive, laborious retraining process.
Exactly. It's a much more flexible way to enhance models.
That really lowers the barrier to applying advanced techniques.
It does. Now, while byte sampler is, a massive leap forward, it's worth noting its current primary focus is on these BPE tokenizers.
Right. You mentioned BPE specifically.
Yeah. Extending it to other schemes like unigram or wordpiece, or integrating it with even more advanced decoding techniques, those are definitely exciting avenues for future research.
And making it handle different pre-tokenization rules more generally, too, perhaps.
Good point, yes. Expanding its compatibility will be key.
Still, a very significant advance.
Absolutely. So there you have it, byte sampler. An incredibly clever and efficient solution tackling that fundamental prompt boundary problem.
Hmm.
By enabling models to operate seamlessly and precisely at the byte level, it fixes those frustrating generation quirks, sure. But maybe more importantly, it opens up this world of new possibilities for combining and leveraging the power of different AI models in ways we just couldn't before, all without changing their core intelligence.
Yeah, ultimately, I think byte sampler's brilliance really lies in its ability to elegantly simplify these complex interactions between models. It makes AI more robust, more versatile, and critically more intuitive for both researchers and everyday users.
Right.
It effectively bypasses that whole obstacle of tokenizer mismatches at a truly minimal cost, letting models finally, communicate effectively.
So as we move forward, and as language models become, well, ever more integrated into every aspect of our lives, what truly revolutionary forms of AI might emerge.
Hmm.
When these models can finally speak and listen to each other seamlessly and precisely across their own internal linguistic boundaries.
It's a provocative thought, isn't it?
It really is. And one that Byte Sampler takes a monumental step towards answering.